Inside a magnetic material, before it achieves uniform alignment, the atomic lattice is a storm of chaotic, localized forces. Millions of atomic magnetic moments constantly push and pull against their neighbors. In an idealized model, like a simple paramagnet, we ignore this chaos. We treat these magnetic moments as entirely independent. According to the Curie law, these isolated moments respond passively to a single external applied field, resisting alignment only due to random thermal agitation. But in real solid-state systems, that independence breaks down. Atoms are packed densely. As they crowd together, the magnetic moments exert strong physical forces on one another, creating an internal environment that easily overpowers any weak external field. Tracking every single one of these interactions is computationally impossible. You cannot map the individual dipole-dipole forces for 10 to the 23rd particles simultaneously. To accurately predict how a bulk material will behave, we require a mathematical shortcut. We need a macroscopic model that bypasses the impossible many-body problem and averages out those chaotic microscopic forces. That mathematical shortcut is Weiss mean field theory. Pierre Weiss recognized that we do not need to track every individual atomic collision. Instead, we assume that a single atomic moment does not strictly feel the external field alone. It experiences a combined effective field representing the average influence of all its neighbors. Look at this vector diagram. The total effective field acting on a moment, H effective, is simply the vector sum of the bare externally applied field, H, plus a new internal interaction field. We call this new internal vector the molecular field, or H-mole. Weiss proposed a crucial theoretical leap to calculate this value. He asserted that this internal molecular field is strictly proportional to the material's bulk macroscopic magnetization, M. This results in the equation H effective equals H plus lambda M. That proportionality factor, lambda, is the molecular field constant. Lambda serves as a direct macroscopic measure of feedback. It quantifies exactly how strongly a material's own magnetization acts back on its constituent atomic moments to force them into alignment. The equation for the molecular field establishes a cyclical, positive feedback mechanism operating within the atomic lattice. This feedback cycle begins when a small external field creates a slight initial alignment of the atomic moments. That initial, localized alignment scales up to create a small, measurable macroscopic magnetization across the material. Dictated by our proportionality rule, the existence of this magnetization automatically generates an internal molecular field. The strength of this generated field is scaled directly by the constant, lambda. This newly generated internal field acts on the remaining unaligned moments, forcing them into stricter alignment. This increases the magnetization, restarting and amplifying the cycle. If lambda is sufficiently large, this feedback loop sustains itself. The material locks into a state of spontaneous ferromagnetism, maintaining its alignment even when the external magnetic field is reduced to zero. We can translate this qualitative feedback loop into a rigorous mathematical derivation to pinpoint exactly when this phase transition occurs. We start with the baseline algebra for independent moments. Magnetization equals the Curie constant over temperature, multiplied by the external field H. To inject the physical interaction into the math, we substitute the bare external field H with the Weiss effective field, H plus lambda M. From here, the algebra is straightforward. We expand the right side of the equation, move all the terms containing M to the left side, and factor M out. Solving for magnetic susceptibility, the ratio of M over H, yields a new equation with a modified denominator, C divided by T minus C lambda. Notice the grouped term, C lambda, in the denominator. We define this value as the Weiss temperature, denoted by theta. This represents the critical temperature scale of the internal interactions. Substituting theta into the denominator gives us the final derived Curie-Weiss law. By simply adding the internal feedback term into the baseline algebra, the inclusion of this variable strictly alters the material's predicted behavior. The equation now maps a critical temperature phase transition where susceptibility diverges, a phenomenon idealized models cannot predict. The Curie-Weiss law is elegant in theory, but it presents a practical challenge for experimental physicists. How do you measure an invisible internal field constant in a laboratory setting? This graph illustrates the standard methodology. Scientists measure the magnetic susceptibility of a material at temperatures far above its ordering threshold. Plotting the inverse of that susceptibility against temperature yields a straight line. The properties of this linear fit provide the internal parameters. The inverse of the Curie constant, 1/c, is extracted directly from the slope of the line. Tracing the line down, the critical Weiss temperature, theta, is identified precisely at the x-axis intercept. With those two macroscopic features extracted from the physical data, isolating the molecular field constant is a simple division. Lambda equals theta divided by c. In a real-world worked example, if a material's experimental data yields a Curie constant of 0.80 Kelvin and a Weiss temperature of 240 Kelvin, dividing theta by c gives a molecular field constant of 300. A lambda value of 300 indicates that the internal interaction feedback is massively dominant. It means the internal molecular field driving the moments into alignment is 300 times stronger than the material's bare macroscopic magnetization. When Weiss introduced the molecular field, his approach was purely phenomenological. He mathematically modeled that this internal feedback occurred without knowing the physical mechanism causing it. Later physicists determined the molecular field's true physical origin lies in quantum mechanics, stemming from the Heisenberg exchange interaction. This links macroscopic bulk material variables to the discrete quantum spin lattice. This formula connects the two domains. In the numerator, the variable J represents the microscopic quantum exchange coupling. A larger quantum coupling strength strictly dictates a larger macroscopic molecular field constant, lambda. Lambda acts as the macroscopic shadow of quantum spin interactions. It enables physicists to use bulk thermodynamic measurements to map out subatomic behaviors. While powerful, we must recognize the boundaries of this model. Mean field theory is a useful approximation, but it is not an exact replica of physical reality. The molecular field is not a literal magnetic field, but an effective parameter for complex interactions. While strictly linked, macroscopic lambda and its microscopic quantum origin J are not identical. Furthermore, mean field theory struggles when local atomic environments vary strongly. Despite these limitations, the chain of physical causality remains distinct. Microscopic quantum exchange interactions dictate the molecular field constant, which in turn establishes the macroscopic Weiss temperature. The molecular field constant remains the primary mathematical tool engineers and physicists use to translate invisible quantum spin interactions into predictable macroscopic phase transitions.